I call this the stoichiometry of gas phase reactions. Typically, this is the first of 3 chapters dealing with states of matter, as you well know. Certainly include solids, liquids, and gases. And this is dedicated to study of properties of gases and how they are analyzed stoichiometrically. There are specific sections on liquids and solids. When we get to chapter 11 in your editing text, it will be states of matter, and we'll talk about the properties of the liquids and the solids in that chapter. But this particular chapter is dealing with the gases. Now, most textbooks will start the gas laws and materials using the empirical gas laws and go through Charles' law, Boyle's law, Gay-Lussac, Avogadro's combined and ideal gas law. I don't do that. Those are tools that are used to solve reaction equations. So I start with the reaction that has all gases in it, and consider this reaction. Here we have a reaction with each component being in the gas phase. There are reactions, of course, with components that are solids or liquids, and then they go to the gas phase, and we'll look at one here in a little bit. But the first question I need to ask you is, what can you determine from this equation stoichiometrically? Well, we should know now we can get moles, equation mass, particle numbers. Those are the first 3 things that we can determine. I add to that from the last section gas volumes. And as we present gas volumes right here, I'm going to turn those lights off. You can see better. I don't know if you can or not. But anyway, gas volumes are now going to be related to what we call molar volumes. Which by definition is the volume occupied by 1 mole of any gas. Now, the first thing you need to understand about this number, gas volumes, it's not always 22.4. When we talk about a gas volume, it has properties of expansion. Very quickly, a gas will expand. Well, you can have a large volume with 1 mole in it, or a small volume at a cooler temperature with 1 mole in it. So when we talk about 1 mole of gas, that occupies 1 mole of gas, it could be a number of volumes. To standardize this number, we say that the standard molar volume at STP is what? Standard temperature and pressure. And we'll elaborate on that in a few minutes. Standard temperature and pressure is, in fact, 22.4 liters per mole of gas. So that is the first thing you need to take into account. The next thing is, how does this information relate to the chemical equation? Well, we know that the coefficients of the equation define the number of moles. We have 3 moles and 1 mole and 2 moles. And if we wish to look at formula weights and equation mass, this one would represent 3 formula weights, 3 formula weights. This one is 1 formula weight. And the last one is 2 formula weights for ammonia. So these items we have already looked at. And you should be able to make calculations based on mass and moles, and as well as particles. Particle numbers refers to Avogadro's number. It's capital N, which is 6.02 times 10 to the 23rd particles per mole. And so if we're talking about, for whatever reason, the number of particles of hydrogen in this equation, we can intuitively say that's 3 Avogadro's number of hydrogen molecules, or 1 Avogadro's number of nitrogens, and 2 Avogadro's numbers of ammonia molecules. Okay, so these things we've already covered in previous lecture. Now, again, we want to add the idea of gas volumes. So 2 things have to happen here that you need to know. One, the definition, obviously. But when we talk about this definition, number 2, in terms of a chemical equation, we assume, just like you assume the 3's and 1's and 2's are moles, you assume that equation is at STP. I don't have to write it out there on the end of the equation, but this is assumed to be at STP. I'll just put equation. Is assumed to be at STP, standard temperature and pressure. So if that's the case, then we can apply gas volumes in this right here, capacity, to this equation. I'll move it up so we can kind of get an idea. So if this is 3, we're talking about 3 molar volumes, 1 molar volume, and 2 molar volumes of ammonia. If at STP, the conditions are at STP, then we can say 3 times 22.4 liters of the hydrogen, or 1 times 22.4 liters represents the volume of nitrogen, or 2 times 22.4 liters represents the volume of ammonia, but only at STP conditions. Because I think many of you already know that if you warm a gas, go above a certain temperature, as you call standard, it will expand. You'll have a larger number. Or if you cool it below a standard number, you'll have a smaller volume. So when this is the first step in understanding gas laws, is that you look at the equation, whatever it may be, and draw your conclusion. Okay, that's its STP, so I can, with no other information, I can literally say at STP this is the volumes based on the coefficient numbers and so forth. However, if you move away from the STP conditions that we have specified here, then you are at non-standard conditions. When you move into non-standard conditions, you have to do something else to calculate the volumes that are generated. Now, in chemistry problems like this, listen to me carefully on this. You always start with the standard conditions, and you work out your volumes at standard conditions. Could you close that door for me? It's kind of loud. Thank you. You always work here. Then you apply the empirical gas laws to achieve the non-standard conditions, or the ideal gas law is the most widely used. You assume your problem starts at the standard conditions, you work the problem at standard conditions, and then move to non-standard conditions. That's the protocol, and we're going to teach you how to do that here in just a moment. Okay, now it's important that you know these, what we mean by standard conditions. That is, what is STP mean? The standard temperature pressure. Now, this is based upon what we call gas law variables, not volumes. Gas law variables. This includes pressure, volume, temperature, and mass. The typical unit symbol for moles is the lowercase n that is listed here. Now, in order to standardize a gas, or the measurements for gas, we choose these gas law variables at specific values. Pressure is considered to be standard at 1 atmosphere, right there, which is also considered to be 760 millimeters of mercury. Okay, I'll explain that in a minute, and we'll give you all the rest of it taken care of. The volume is the standard molar volume at STP, which is 22.4 liters. Okay, if you're at standard. If you're not, it's a larger number. If it's below standard, it's a smaller number. The temperature is 0 degrees Celsius, which is also 273 Kelvin. And when working gas law problems, for the most part, you will always convert to Kelvin. Always convert to Kelvin before you work your gas law problems. There are some energy problems where you don't need to do that, and I'll show you those when we get to thermochemistry. And this, of course, is all related to 1 mole. So with 1 mole of whatever specified gas you choose, it is 0 degrees, 22.4, 1 atmosphere. Okay. Now, this is for 1 mole of gas. Now, the issue is primarily going to revolve around how does volume and mass relate in the relationships that you'll see here. If you decrease the mass, say, to 1/2 mole, well, your volume will decrease by half. So if we have moles in at STP, for example, 1, well, the volume, 1 mole, will be 22.4 liters. If the problem is presented to you where it says 1/2 mole, well, that's 11.2 liters, okay? Or if you have 2 moles, you'll have 44.8 liters. So all of these now are at 0 degrees and 1 atmosphere. So you can calculate, based on the mass you have, a volume. Okay, so if it's 1 mole, you can count on it being 22.4 liters. But if it's 1/2 mole, it's half that. If it's 2, and so forth. So you can scale it up or down if you are, with respect to the 22.4, if you're at 0 and 1 atmosphere. But again, if you depart that, you go to non-standard conditions, and that's where we have to use the empirical gas laws. Now, using the empirical gas laws, why do you use them in the first place? Okay, well, to solve chemistry problems is probably one of the ones you're most familiar with. Somebody give you a Boyle's law problem, a Charles law, or something, but if you haven't been indoctrinated as to their function, they're primarily used to convert from standard conditions to non-standard conditions. Using the empirical law, converting from STP to non-STP conditions is the primary objective. The empirical laws include Boyle's law, Charles' law, Gay-Lussac law, Avogadro's law, combined gas law, and finally the ideal gas law. So it's our primary objective, is to learn how to apply these to chemical equations that produce gas phase products or have gas phase components going in as reactants. I'll tell you what these are related to. These are proportional to the gas law variables. And I'm going to show you how they're develop them and show you how to use them in just a moment. But Boyle's law is a pressure proportional to a function of volume issue. As a matter of fact, it's an inverse relationship. Inversely proportional is another term that's used to describe that. If you increase volume, you decrease pressure. Here is a syringe with a specific volume in it right here. Now I have equipment that will specify, but if I close the tip of that and push this down, the plunger is hard to push any further than that. I'm using all I got to push it down. Now if I pull out on the syringe, my finger starts sliding into the hole there. So anyway, this is the idea of Boyle's law. It's an inverse relationship. Decrease volume, you increase pressure. Now these are intuitive things that I think everybody has had some normal experience with, okay? And if I increase the volume, I will have a decrease in pressure. So this is the first empirical gas law. When we say empirical, we relate the variables to what we are observing. What I have not mentioned in this effect, and I think you could probably, if I ask you a simple question like, well, why is the pressure increasing or why is the pressure decreasing? Yeah, I think most of you probably say, well, the particles are hitting harder and make more pressure. Well, that's what I have not mentioned in the empirical issue. The empirical only relates to observable macro level conclusions like increase or decrease, the other one increases or decreases. Well, in this context, this is an inverse relationship. Well, this, and I want you to check this, write this in red if you have to. Boyle's law is the only inverse relationship of the empirical relationships. It's the only one in there when you compare this. Now, we haven't mentioned temperature and mass. This is considering at a constant temperature and constant mass. I didn't add anything to the syringe and I didn't take anything out of it. I just moved the plunger. Charles' law, Gay-Lussac, Avogadro's combined law, ideal gas laws are all direct relationships. And so when I talk about Charles' law, it's temperature volume. Temperature proportional to a function of volume. That is temperature proportional to volume. And that's a direct relationship. This is not difficult to understand if we consider this volume in the syringe right here, and I heated it and closed it off the end with constant mass, constant the pressure, so the pressure would stay constant. It would increase in volume. So if you heat a gas, it increases in volume. If you cool a gas, it decreases in volume. So that's the essence of the relationship in Charles' law. Gay-Lussac law is, I like to say, gas in a box. And it relates temperature and pressure. Temperature proportional to a function of pressure. That is, temperature proportional to pressure. It too is a direct relationship. If I have a gas that's confined in a box, a steel box, a pressure cooker, and I heat that, I think we all will agree the pressure would go up. If we cool it, pressure goes down. So one goes up, other one goes up. One goes down, other one goes down. Direct relationship. So that's your Gay-Lussac law. Avogadro's law deals with blowing up the balloon. That's a mass volume issue. So we say mass proportional to a function of volume, where N is directly proportional to volume. You blow up a balloon, what are you doing? You're putting more mass into the balloon. I meant to bring a balloon this morning, but I've got it. Anyway, you blow it up, gets larger, and when the mass comes out of the balloon, it gets smaller. So these are your empirical gas laws that relate two of the four variables. When you get down here to the combined law and the ideal gas law, these are related, those laws are related to all of them at the same time. Okay? And so I'm going to hold off developing those until I show you a couple of relationships and a couple of problems on the regular gas laws here. The first four gas laws. Boyle's law. Now, again, this is the only inverse relationship. It's pressure proportional to 1 over V. Now, listen closely to me, because this will come up several times throughout the semester in which we have to take variables and set them to equal to one another in an equation. We need an equation out of this thing. Now, in order to make an equation from a proportionality, you know pressure is one thing and volume something else in terms of its physical capacity and what it is. But I want to relate the two in a mathematical relation. We insert what we call a proportionality constant. So if I want to make pressure equal to some other variables, I put a constant in, which we call a proportionality constant. And that does make it equal. It's like 6 equals K times 2. What's K? Okay, so the constant's always 3 for whatever we do. So we don't really know what that K is. I mean, we will shortly know what the constant is, called a universal gas constant. We will work with it. But this is the relationship. Now, consider two conditions. Okay? Here is a cylinder with plunger in it. And we'll call this pressure 1 and volume 1. Okay? And this will be case 1. And then we would go over here, and you could either pull it out or push it down like I did the syringe. We're going to push it down for our demo. And of course we'll have a second pressure and a second volume. And this would be, of course, case 2. Now, the one thing we can say about the relationship between pressure and volume is that pressure is proportional to K1 over V. And I can solve this for K to equal pressure times volume. In case 1, we have a constant. And what does constant mean? Unchanged. K2. Well, these are equal. and they adjust themselves numerically to keep that K value at the same provided temperature and mass constant over here. So if K1 equals pressure 1 times volume 1, then we can set that equal to K2, which is also a P times V, but P2, V2, like that. This is the empirical relationship for Boyle's law. Now, in the problems, they'll give you 3. You solve for the unknown. Say you're given pressure 1 to equal to 720 millimeters mercury. I'm going to use it that way. Volume 1 is 3.8 liters. Pressure 2, say you squeeze it to a higher pressure, 1,050 millimeters of mercury. Pressure goes up, okay, and we calculate volume 2. So you extract those numbers into a little data table and apply it to the empirical relationship. So in this case, P1 times V1 equals P2 times V2, and since the question is V2, we solve for V2 is P1 V1 over P2 and substitute the values. P1 is 720 millimeters. Volume 1 is 3.8 liters, and the pressure 2 is 1050 millimeters of mercury. Notice the millimeters of mercury will drop out, and we're left only with volume numbers, which is, so I get 2.6 liters out of my calculator. Y'all check back, keep me honest, check on that. Is this a reasonable conclusion for this type of problem? Okay, based on the theory up here, if we increase pressure, we have to decrease volume. So we see in this relationship, we have an increasing pressure. As a result, this must decrease. So it makes sense. Now, if we punch it in the calculator, I'd give you credit for it. So that's one of the empirical laws. Okay, Charles' law, as we've already mentioned, is a volume temperature relationship. That is, volume is proportional to a function of changing temperature. So our two variables are volume and temperature. And we put pressure and mass. You'll see a lot of symbology with the constants as subscripts in the symbology. Well, we can simply say volume is directly proportional to temperature, and again equate these and solve for K, and we have volume over temperature. So we can take again a case 1 scenario and a case 2 scenario, set them equal, case 1, case 2, pressure and mass staying constant, and we can solve for the unknown. You have to be given 3, or the ability to calculate at least 3 of the variables. So if we use a quick analogy here, we start out with volume 1 and go to volume 2. Let's say we heating, we should expect volume to increase. So this is at T1, and of course this would be at T2. Okay, So K, again, is constant for the ratio of volume to temperature, as was shown over here. So that'd be K1 is equal to K2. And so we could take V1 over T1 to equal V2 over T2. And so this is the empirical relationship that we developed for Charles' law. Okay, here's an example, and it has two purposes. One, you've got a 0 degrees in here, and if you substituted 0 in for T1, notice that you'd be dividing by 0. That's not allowed. So we have to convert this to Kelvin. So we add 273 to the Celsius number, and it's 273 Kelvin. That's the one that must be substituted into the value for temperature 1. Now temperature 2, well, you can't work Kelvin against Celsius, so you have to convert it also, adding 273. And so you have 283 Kelvin now. And so you have the 3 data points that you need for V1 over T1 equals V2 over T2. And we're looking for V2, which is V1 T2 over T1, and substituting V1 is 380 milliliters. T2 is 283 Kelvin and 273. So we're not dividing by 0 now. So 394 is what I get out of my little calculator. And again, does this make sense with respect to what's happening? Okay, so we're going from 0 degrees to 10 degrees, so we have an increasing temperature. Our expectation is that this would increase also. And so we started 380, went to 394, so the logic holds up as far as Charles' law goes. Okay? And this, again, is a pressure temperature issue. That is, pressure is proportional to a function of temperature, and again, it's a direct relationship. It's a gas in a box, or something that's confined and not allowed. A pressure cooker, if you need to have an analogy. This would be pressure directly proportional to temperature. Increased temperature, increased pressure. And again, to make an equation, pressure is equal to K T, and the K value for conditions 1, condition 2, or case 1, case 2, however you wish to present it, is pressure over temperature. So K1, case 1, you can draw a picture if you wish. K2, which gives us pressure 1 over temperature 1 is equal to pressure 2 over temperature 2. So if we are given a pressure 1, say at 35 millimeters of mercury, like that, I'm just making up numbers, okay, and temperature 1 is 10 degrees Celsius, what would be the pressure if we change the temperature to minus 20 degrees Celsius, like that? So step 1, of course, is work all the gas law, empirical gas law problems in Kelvin. So we need to add 273, and that's 283 again, Kelvin, or we add 273 to that one, 253 Kelvin. So now we have the 3 of the 4 values we need, and again we solve the expression for P2, and so I'm just going to bring it down here to P2, save us some space, is equal to P1T T2 over T1, if that's okay with y'all. Pressure 1 is 35 millimeters. Temperature 2 is 253 Kelvin divided by 283 Kelvin. Kelvin drops out. Now, what do we expect to happen based on the proportionalities here? Well, I've got 35 millimeters and I'm going to cool it. I'm going to decrease my temperature. What do I expect this to do? It should decrease also. Everybody good? All right. Now, that looks like 31.3 millimeters. Now, for the gas laws, you're going to have to work problems like this, and there's really an easier way to do it once you write in your data points. Let me show you this. Okay. Looking at a problem like this, say you just extracted the numbers out of a written problem, and you jot them down, P1, V1, T1. You can tell who's first and second and that kind of thing very easily by reading the problem. I think it'll be obvious. What's going to happen? What do we expect to happen? All right, the pressure is, as shown, increasing. Now, this is a Boyle's law problem. It's an inverse relationship. So what do we expect to happen here? Decreasing, yes? Everybody good? All right. Well, that gives us two options to get the second volume. Volume 2. Okay? It's going to be related to volume 1, 21.8 liters. 21.8 liters times the pressure ratio. Now listen to what I'm telling you. You're noticing a decrease. And all you've got to do is set up a pressure ratio between these two numbers. 3.5 atmospheres versus 4.3 atmospheres, so that we wind up with a smaller number. Is that what we're supposed to get? Smaller number? Hey, come on. Yes? Everybody understand that? Okay, so if I'm going to get a smaller number, which of these, A or B, should I use? 3.5 atmospheres over 4.3 atmospheres, or 4.3 atmospheres over 3.5 atmospheres. Which one do I use to make this smaller? This one, A or B? A. Everybody see that? Mm-hmm. See, this is a fraction. And fraction times that's going to make a smaller number. Everybody good? Okay. So this would make a bigger number. And so we don't want to use a ratio like that. So you can do this for all of the empirical. Okay. This ratio winds up as 0.8 or 8/10 of what we started with. So this is 8/10 of 21.8 gives us a smaller number, 17.8 liters. And it is logically in line with the theory and proportionalities that we're looking at. Now we get into the combined gas law. Okay, and this is where we take all the proportionalities and we line them up and see the relationship like we did with the two variable relationships. Okay, I'll show you. Pressure proportional to 1 over volume, okay, as Boyle's law. Volume proportional to temperature, Charles' law. Pressure proportional to temperature, Gay-Lussac law. And Avogadro's law, mass proportional to volume, blowing up the balloon. I didn't go through an example of that, but it's the same thing, mass, moles, and so forth. Well, I want to relate pressure and volume. So I'm going to come over here and I'm going to say pressure is proportional to 1 over V, like that. Well, when I look at this one, I see volume proportional to temperature. Okay, directly proportional. So I'm going to do that. So they're proportional. And pressure and temperature, well, I'm just going to come in here with that. So I have pressure directly proportional to temperature. I have temperature directly proportional to volume. And I have pressure inversely proportional to volume, as I've written it. See how that works? Same scenario. How do I make this come together as an equation? Just like we did all three equations before, we insert a proportionality constant. Pressure over temperature is equal to, we're going to call it R this time. R value is called the universal gas constant. Temperature over volume. Okay, wait a minute, I forgot mass. I got temperature and mass. I need an N. What am I? These are. Okay. Now, we can't have both sides, so I'm just going to cross that one out, make that one a 1. So the outcome of this is PV equals nRT, and this is called the ideal gas law. Now R is always the same if you're at a specified temperature and pressure. R is going to be one value, and if you change the temperature, pressure, and volume conditions, you change R value. But to keep R, say case 1, we got R1. Case 2, we have an R2. So if I solve this for an R, right here I'd have PV over NT, case 1. And this one would be PV over NT, case 2. Now what I'm showing you guys is you'll have problems where everything changes. And you'll be given 1, 2, 3, 4, 5, 6, 7 values possibly in a problem. And you solve for, say, one unknown, or have a way to calculate all 7 variables in there. Now, for the most part, problems will come to you with constant mass. And so with this constant mass between the two here, and R1 equals R2, then we have P1 V1 over N1 T1 equals P2 V2 over N2 T2, like that. At constant N, we have PV over T1 equals PV over T2, like that. This is the most used combined gas law. As I start this, when you get a problem that you recognize as an empirical gas law, whether it's Charles' law, Boyle's law, Gay-Lussac laws, whatever, Avogadro's law, start out with a PVT, 1 and then 2, just like that. I always put the T at the bottom. You could put an NT down here if you're having masses, but we're going to hold that until I get to the PV equals nRT. Okay, here's the deal. We're going to find a new volume, okay? Volume 1 is, say, 30.7 liters, whatever. Okay? Pressure is 840 millimeters. And temperature 1 is 25 degrees Celsius. Okay, so you pull these out and stuff them in your data table. The problem will be verbal, and you can recognize who's set 1, who's set 2. And pressure 2, let's go to 10, 15 millimeters of pressure at a temperature of 30 degrees Celsius, like this. Now, again, even this you have to convert to Kelvin. That's why I put this at the bottom, so I can put my 273 under the number, and 298 Kelvin and 303 Kelvin. Okay. Now, watch how I do this. From what I've taught you so far, you don't have to remember proportionalities or the name proportionalities, but you do need to remember what's inverse. Boyle's law is only one, pressure volume. Everything else is direct. We want to calculate a volume 2. Well, volume 2 is going to equal volume 1 with a temperature pressure correction. Just like I showed you in the previous example. All you have to do is decide on what the volume's going to do overall, and do that for each one. First do a temperature ratio or pressure, it doesn't matter, and then follow with the other one. Okay? So if we look at this, what is going to happen, what do we expect to happen to this volume if we change this pressure, up or down? Okay, if we go up in pressure, we go down in volume. Yes? Everybody good? All right. So I want to take these two and make a fraction out of them so that my V1 will go down. Does that make sense? You want it to go down. So I'm going to, that's a 50. I'm going to take 840 over 1015 millimeters, like that. If I put 1015 over 840, it would create a bigger number, which is wrong relative to Boyle's law. I do the same thing with temperature. Now you're through with pressure. Forget it. Now apply temperature relationship to what's going to happen to V1. So we see a 298 to 303. Well, that's an increase. So I want V1 to increase now. So I'll take a ratio here, 303 over 298, and I know that will increase that. Now, regardless of what pressure factor is, you're through with that. Each one adjusts itself. So all I have to do is put the 30.7, then 840 over 1015, 303 over 298, and everything's going to come out in liters. 25.8 is what I get. Y'all back me up now. Okay. If you are faced with significant figure issues in something of this nature, base it on the unknown, data of the unknown. You're given 3 significant figures. That's enclosed zeros, that's 1, 2, 3. You want to round your answer to whatever the unknown is. Okay? When we talk about chemical reactions, equations, we assume reaction at STP conditions exist, which is 0 degrees Celsius, 1 atmosphere. Well, if that's the case, then the volumes or molar volumes are standard at STP, which is 22.4 liters per mole of whatever gas you have. Okay? So this relationship is applied to whatever equation we want to work with in the problem set. Let's try and use the magnesium. We'll do this in the near future. Plus a couple moles of hydrochloric acid. This will give you a magnesium chloride aqueous plus hydrogen gas given off, like that. Now, if we had 25 grams of magnesium given, and an excess solution of hydrochloric acid, okay, and more than we need. What volume of H2 will we generate out of this? Okay? Well, from the equation, what does it tell us straight off? Okay? 1 mole of magnesium solid gives 1 mole of H2 gas. That's what the thing says straight away. So what is the volume of 1 mole of H2? I guess that's an H in there somehow. 1 mole of H2 gas at STP conditions. What is it? Are y'all staying with me now? Come on, man. I know this is not the most exciting way to spend your day, but 22.4. We okay? Anybody got a problem? Okay, so 1 mole will generate 22.4 liters right there. So that's what the equation says. But we only have 25 grams. Convert that to moles. Well, what's magnesium? I don't know. 24 or 23, something out there. Look it up. 24. 24 grams per mole. Okay, so we have 25 grams divided by 24 grams per mole. Remember, I always told you, work the problem in moles. If they want something else later, work it back. Convert back. So it's 25 divided by 24 is 1.04 mole. Okay? What volume in liters is that? Well, it's a ratio. It scales from the 22.4 up. It'll be bigger than 22.4 because you're using more mass. Make sense? I mean, it's just a logical proportionality. So 1 is to 1.04 as 22.4 is to x. So x is going to be bigger than 22. Not much, but based on the numbers I picked out, x is equal to 1.04 times 22.4. It'll all come out in liters. And that's 23.3 when everything is said and done. Okay, we'll take our same issue and same issue, 25 grams. Okay, and we want to know how many liters will be generated. But I'm going to give you a different set of variables now. Pressure, volume, temperature, and mass is what I'm going to give you this time. And if we, let me do it this way. This is case 1. Okay? Case 1 is going to be STP. I'm going to put STP right there. So that's 1 atmosphere. Volume for 1 liter, 1 mole. I'm going to go with 1 mole of gas. That's going to be 22.4 liters. We could use the, no, I'm going to stay with this. And this is 0 degrees Celsius, which is 273 Kelvin. Okay, non-STP. Okay, P2, V2, T2, and N2. Okay? What's happening here is you're starting with a standard set of conditions, and leave it cracked open so I can get back in. Okay? And you want to calculate the second set of conditions. Primarily the volume is usually the one that shows up as your need. Let's try 740 millimeters of pressure. We'll take 25 degrees Celsius, and it's 25 over 24 mole. Okay? Now, as you look at the data and track, you have to have compatible data. I think you know that. So if I'm in atmospheres over here, this needs to be in atmospheres. Well, this is equal to, and you can put this on your notes, 740 over 760. If you take whatever you're given in millimeters, divide by 760, you'll have it in atmospheres. Okay, so that's a pretty easy conversion right there. Okay, this needs to be Kelvin, 298 Kelvin, and we were at 1.04 mole here. Now I can do one or two things here. I can use the combined law, case 1, case 2, or I can use the ideal gas law. Now how does the ideal gas law relate to the combined law is the question. All right? We already know we have case 1 and case 2. PV over NT equals PV over NT. Okay? So P1 V1 over N1 T1 is equal to P2 V2 over N2 T2. No matter where we go in the universe, if we identify the standard conditions, it's going to be pressure is 1 atmosphere, volume is 22.4 per mole for 1 mole, and temperature is 273, 0 degrees. Everybody understand that? If I say standard conditions, 0 degrees, 273, 1 atmosphere, okay? Volume 22.4 for 1 mole. If you put those numbers in P1 side, B1, C1, you'll get a constant, regardless of what side 2 is. The variables will be mass and volume. So I could cut this in half, I could cut this in half, right? Remember I told you at the beginning of class, you can cut those in half? If I double this, double that. But one thing that doesn't ever change is the R value, is whatever constant comes out here, and that's why we call it an R value. I'll bring this up. If I take P1 as 1 atmosphere, V1 is 22.4 liters. Now that relates to 1 mole at 273 Kelvin. Now, to apply the variables of volume and mass, I want you to watch this. 1 atmosphere, we're still at 1 atmosphere and 0 degrees, but I'm going to cut this in half. And I'm going to cut this to 0.5 mole and 273 Kelvin. Or if I double it, 1 atmosphere and 44.8 liters over 2 moles and 273 Kelvin. And you can go and put it in your calculator. See how I changed the volume and moles in each case, but the temperature and pressure stayed constant through there. That's always standard. All 3 of them will be the same number. What we do is we call this the universal gas constant, the R value. And we substitute that for PV over NT1 so that we get R, which is case 1, you can put a 1 down there to remind you, is equal to P2V2 over N2T2. This can be simplified to be PV equals nRT, where you keep in mind PVNT is always case 2. R is going to, no matter what you do, is always going to be 0.08206 if you use standard conditions. Volume and temperature, well, volume and mass, I'm saying, will adjust themselves, but they'll always give you 0.08206. So we can take our problem up here to calculate the pressure at non-standard conditions and apply it to PV equals nRT and solve for V to equal nRT over P. And these are twos. And so all you have to do is have case 2 right here and plug them in, and you've got your new volume out of your ideal. Now what I want you to learn here is how the combined law, that's how I developed it, proportionalities, relates to the ideal gas law. PV over T equals PV over T. Well, the P1 V1 over T1 N1 is R value. So you can just put R there, the same number every time, and then fill in your data, solve for whatever they're asking you for. Whenever you're looking for volume 2, I'll come down here. Volume 2 is 1.04 mole, 0.08206 liter atmospheres over mole Kelvin. Temperature was 298 Kelvin, and pressure 2, what did I say? It was 740 millimeters, 740 over 760 in atmospheres. And you punch that into your calculator, and you have the 26.1. Okay? All right. Take this and calculate the V2. Okay? It can be done either by PV equals nRT, because see, everything here is I pull this off for 25 grams at standard. Okay? And put it into PV equals nRT, or we can go PV over T equals PV over T and use the proportionality relationship. I'm going to use that one and the PV equals nRT. Okay, what's happening here and what's happening here is we are decreasing, because one atmosphere is 760 millimeters. Now you can solve this combined law in millimeters, because as long as you keep the units compatible. I'll do that just for relations, show you. So we want V2. Now here we're increasing, so we expect an increase in volume. Here we're decreasing, so we're decreasing volume, increase in pressure. So we want to go up in pressure here. So V2 is always started out equal to V1, and then we put the pressure temperature corrections based on the proportionalities. Okay, we'll go with this one first. So you decrease pressure, okay, increase volume, right? So if we're decreasing pressure, we're pulling the plunger out. So we want to increasing volume, so I need to put 760 millimeters over 740 millimeters. Okay, everybody good? Okay. And then finally, what's happening here, of course, that's 298, sorry. 298 Kelvin, this is 273 Kelvin. So we're increasing temperature, increased volume, so I want a big number over a little number. And so we substitute in here the volume 1, 23.3 liters at standard conditions, 760 over 740, and 298 over 273.
Why is it 760 over 740?
We're decreasing, we should increase pressure. Same thing as we got before. But we use the ideal gas law up here in our first example. But here we just use proportionalities in the second one.